Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at inverse functions. So let's start with the definition. Definition, inverse function. An inverse function is basically a function which performs the opposite operation to that performed by the original function. So this definition could do with a bit of unpacking. So let's actually look at some remarks to try and better understand this definition, right? So the first thing is the inverse function is actually a function. So it is a function. The second thing to keep in mind is it is defined by contrast to another function. Okay, so you've got to have some function defined first, and then you can define what's called the inverse function. So it is defined in contrast to another function. And the third key thing about it is it actually does the opposite to the other function. So let's call that other function the original function. So we say it does the opposite to the original function. So let's think about notation and try and incorporate the points that we've actually mentioned above. So let's define some original function. Okay, so let's take y equals f of x to be our original function. And of course, what does this actually tell us? This tells us that our x is actually the input and our y is actually the output. Okay, so schematically what's happening is we've got some input and then we've got the function f acting on it, and then we've actually got some output. So now to say that the inverse function does the opposite of our original function, it's actually going to swap the roles of the input and the output. So in other words, if I actually do it in a different color, so if you actually give it the output, it's actually going to take that back to the input, okay? And of course, we have to give a name to our inverse function, so I've got to write that here. But because that inverse function is basically the inverse function of f, so it's not surprising that it's going to have the name is going to be something like f, but I can't just leave it at f because then we're going to be confused between this f and this inverse function. So what we actually do is we actually usually put a -1 on top, and that tells us that actually, so it's related to f, but it's not quite f, it's actually the inverse of f, okay? So this is what the inverse function does. So let me write that here. The roles of input and output are swapped. So there is a better way of actually drawing this schematic here, right? And the better way is as follows. So what you might actually have is you might have x, and then you might have f acting on x to give us y. But then because inverse function takes you back to x, rather than have the schematic laid out like this, what we could actually do is we could actually go backwards. So we can say the inverse function actually does this. Okay, so it takes in the output and it gives us back the input. So you see what the inverse function has done. It's basically taken us back to where we started from. So the way to write this down is to say you start with x, you apply f to it, right? So this is basically f of x, which is obviously another way of just saying y. And then if you apply the inverse function to that, right, we apply the inverse function to the whole thing, then what we actually find is, applying inverse function to that, we come back to where we started. So we actually have this. So this is a defining feature of inverse functions, the fact that they satisfy a property like this. So let me just say that here. So inverse functions undo original functions. Okay, and we can see the undoing actually happening here, as I've said. So the function does something to give f of x, but then the inverse function just undoes it and gives you back what you started with. I should actually really clarify this point, which is when we write f to the -1, we need to be very careful as to what it is we're saying, okay? So the convention is when we write f to the -1, we don't mean 1 over, okay? So this purely means inverse. So in other words, this thing here is the inverse function of f, and this is not the same thing as f of x all to the power of -1, right? Whereas this thing here will have the meaning of the usual meaning of the power of -1, which is 1 over, okay? So you really need to be clear on that point, and let me write NB here actually, just so there's absolutely no confusion. Right, so there is lots more to say on inverse functions, so let's make a bit more room and continue our discussion. Before looking at more theory on inverse functions, let's quickly consider a very simple example. So say I've got a function, and that function basically just doubles the input to give me the output, right? Now, suppose I want to write down the inverse function. Well, it shouldn't be too hard for us to figure out that if the original function is basically taking some input and doubling it, then what I want my inverse function to do is to do the opposite of that doubling, which means I actually want it to halve the input to give me the output, right? So I've basically got my inverse function, but we need to check that this actually is an inverse function. And of course, we figured out this property that actually inverse functions satisfy this condition here, right? So we're gonna check to see if this condition here is satisfied. So this is fairly straightforward. We just work out this composite function. So we just say f inverse of f of x is exactly the same thing as f inverse. Well, we know what f of x is. That's just 2x. And we also know what f inverse actually does, right? It takes in an input and it just halves it. So my input happens to be 2x. I'm just going to halve my entire input of 2x, and lo and behold, we get exactly x, right? So in other words, since this condition is actually satisfied by all inverse functions, and we see that this function we've called f inverse actually satisfies that condition, then that is definitely the inverse function of that. Now, here's a bit more of theory, okay? So fact one about inverse functions. Not every function has an inverse function. In other words, there are some functions that are not invertible. Now, to understand this a bit further, we need to develop other ideas. So let's do that. We might have something like the domain of f. And of course, then if f actually happens to act on the domain, then we actually end up with the corresponding range of f. Okay, but as we've already seen, because the inverse function is going to do the opposite, it's going to do something like this. It's actually going to go the other way around, and that's our inverse function, provided it actually exists. And what we're seeing is this thing here now happens to be the domain of our inverse function. And as a result, this thing here actually is the range of our inverse function. Well, you shouldn't really be surprised by this because this is really the input to our inverse function and this is really the output to our inverse function. So that has to be the domain of the inverse function and that has to be the range. But also this was very predictable because we know that the inverse function swaps the roles of input and output, and that's precisely what's happened here. So maybe let me write that down sort of more formally. The domain of f inverse is the same as the range of f. The range of f inverse is the same as the domain of f. Okay, so now with that, we can start to think a little bit more about when are we going to have inverse functions existing and when we're not going to have inverse functions existing. So let's make a bit more room and continue with that. So really what we're looking for is some criteria to determine if a function is actually an inverse function. So criteria for invertibility. Okay, so let's actually think about mappings for a moment. So let me say types of mappings, and you'll see why this is actually important because we know that mappings are basically real functions, and we've already categorized mappings into various categories, and they're as follows. So one category might be one-to-one, another one might be many-to-one, and a third might be one-to-many, and the last could be many to many. Okay, this is every single possible way of categorizing mappings. Right, so we know that basically anything that actually ends with many, so let me maybe highlight that. So anything that ends with many cannot possibly be a function, right? So not a function. And we've already looked at this, and of course the reason for it is because a function has to give one output. So if something is giving many outputs, it can't be a function. But now the advantage of actually writing this down is as follows. I could now go on and say, since these types of mappings are not actually functions, then according to the definition of an inverse function, they cannot possibly have an inverse function, right? Because to have an inverse function, you have to have a function first, and then you define an inverse function with respect to that function. So in this case, since these are not functions, they cannot possibly have an inverse function, right? So cannot possibly have inverse functions. Good. So we've managed to basically half our workload. So now we just have to think about these two cases, and we need to be a bit careful. So let's think about this case here. Uh, so we know that a many-to-one mapping is basically another way of saying it's a many-to-one function. In other words, many different inputs can map to the same output, and that's completely fine because each input would still have just one output. But the important idea here is that actually the thing we have here is the domain, and the thing we have here is the range. So let me maybe say that. So I could say this thing here is the domain part, and this thing here is the range part. Now, I should say we do know that this thing here is a function necessarily, so that's fine. We can give ourselves a tick. But let's now think about the domain and the range more carefully. We know that when we actually go and consider the inverse function, actually it swaps the domain and the range, right? So let's think about what's going to happen when we swap the domain and the range. We're going to basically go from many to one to many. Okay, so that's going to give me something like here, say, it's going to give me one to many. And now we have a problem. So the problem now is we've got many things coming out for apparently, one input. And that's not okay. This again violates the definition of a function. So I should say not a function. So what we have here is this case describes all the various possibilities where the thing you start with is a function, but somehow when you go to invert it, the thing that comes out is actually not a function. So I will give an example of this very quickly, actually. So let's consider this. So let's say, e.g., many to one. So you might have something like f of x equals x squared, right? And the graph obviously looks like this. So you've got this sort of a thing here, right? And this is obviously y and this is x. And you've got, say, you could have 2 and minus 2 both mapping onto, I don't know, 4 here, right? So when you actually go to work out the inverse function, you might say, well, because we're squaring, the inverse function might actually be sort of square root, because square root is the opposite of squaring. So the inverse function might be the square root of the input. So yeah, there is some merit to thinking like this, but the problem is the minute you take a square root, it throws out two numbers in the formal sense. So technically, actually, this thing is not a function. So it cannot possibly be an inverse function because an inverse function has to be a function, right? So this is an example of where you've gone from many to one to now having something which is one to many. And of course, as a result, not a function. So there are actually ways around this sort of a problem, and perhaps we can sort of discuss that in more detail later. But let's now return to our initial case, which is one-to-one. And as it happens, this is actually a perfect case where an inverse function will always exist. So let me maybe write that here. Inverse function always exists. Now, that shouldn't be too hard to figure out as to why that is, because obviously for each input we have each output, but each output is different. So when we want to go back, we know, for example, which output is going to go back to which input because the inputs and the outputs are paired up in a unique way. Whereas in this case here, the inputs and the outputs are not unique. So once we've got, for example, many things going to the same output, if we want to go back from that one output to back something in the input, we don't know which particular one of those many inputs to go back to, right? And since that's never the case here, we can always do that and the inverse function will always actually exist. Okay, so we now have a criteria for knowing when a function is invertible. So a function is actually invertible only when it's actually one-to-one. So let's write this down as fact 2 actually, right? Every one-to-one mapping let me say slash function is invertible. And in fact, the advantage of doing all of this is we've also been able to prove fact 1, which is we can now see that there are entire groups of functions that are actually not invertible. I mean, these things are not functions, but there is an entire group of functions which is not actually invertible. Okay, so facts 1 and 2 have now been proven. Let's go on and develop more theory. So continuing with the theory, the thing we actually need to be aware of is actually what I'm going to call fact 3, right? Which is the graph of the inverse function can be obtained from the graph of the original function by just reflecting about the line y equals x. Okay, so let me write that down. The graph of the inverse function can be obtained from the graph of the original function by a reflection about the line y equals x. So let's try and understand why this fact is actually true. So suppose we start with the function f, right? And suppose we have the point AB. So here, A is our input, of course, because we put our input in the first location, and then B is our output. So we get A, we put it into F, and we get B. That's completely fine. So now suppose we actually go and look at F inverse, right? And we want to consider the same sort of point in some sense, right? Well, what's going to happen? The input and the output are going to get swapped. So in other words, I'm basically going to get this, right? So now if I do it in a different color, this actually happens to be my input. And this actually happens to be my output. And of course, unsurprisingly, this was the old output. And this thing here is the old input. Okay, so let's think about what happens when we plot both this point and that point on the same coordinate system. Okay, here's a diagram to basically help us think. So if we now think about this, so let's take this point here to be AB. And what that basically means is this distance here is A, right? And then this distance here is basically B. So I'm going to go A across and then I'm going to go B up, right? But now if I want to plot BA, that means I'm actually going to go B across. So in other words, that distance there is the distance I actually want to go across, right? So we see I've gone across that distance here. So that's B. And then this distance here, which is how much I was going across before, is actually the distance I actually want to be going up, right? So let me mark that. So I hope it's now crystal clear that actually if I take the point AB and then want to also plot the point BA at the same time, they're actually going to look like this. And it shouldn't actually come as a surprise to you that actually this is basically the same thing as a reflection about the line y equals x. Because if I draw this thing here, and if I draw that thing here, you will see that actually what's happening is we actually have something rather nice, which is the triangle which we have here is precisely the same as the triangle we have here. And we can do, I mean, that's sort of obvious just visually, but if you really wanted to go away and think about this a little bit more, you can do that and you can actually start to put numbers in and so on and so forth and figure out that this is actually true. So this line in the middle is actually the line y equals x. So now what we've shown so far is if we actually swap the order of our input and output, so we go from AB to BA, then actually that's the same thing as a reflection about the line y equals x, okay? But if we now consider what we've done, we actually started with a general point on the function f. And this thing here is a general point on the function f inverse. So in other words, this behavior that's happened, so this reflection that's actually happened, is going to happen for every single point on the function f. And therefore, another way of saying that is, we can reflect the entire function f about the line y equals x to get the graph of the entire function f inverse, right? So we've now proven our fact 3. Fact 4 is actually another very interesting fact, which is the inverse function of the inverse function is actually the original function. So the inverse function of the inverse function is the original function. So what do I mean by this? I mean, before we actually did this, didn't we? Before we said, you know, you can start off with some original function and then you can actually go and figure out the inverse function of the original function. And part of the definition of the inverse function that actually it has to be a function, but it has to do the opposite of some other function, okay? So we start with some function and then we work out the inverse function. But now what I'm saying is, actually, this inverse function here I've got is itself a function. So why not we start with this function here? And let me write it like this maybe, just to emphasize that I'm thinking of this not necessarily as an inverse function, but I'm thinking of this entire thing here just as a function in its own right, okay? So now I've got a function. Now I want to go and work out its inverse function. So I want to write that function again, and I want to put a -1 here, right? That's how we write inverses. And of course, it's a function of x. So the question now is, well, what's this function itself going to be? And fact 4 tells us the answer. Fact 4 tells us that this is nothing other than the function f of x itself, okay? And why is that the case? It is the case because of fact 3, right? So I can say this here. True because of fact 3. Okay, so what do I mean by that? What I mean is fact 3 tells us to get the graph of an inverse function, you reflect about the line y equals x. So by fact 3, to get the graph of an inverse function from the graph of a function, we reflect about the line y equals x. Okay, so now imagine this. So imagine we start with f, we reflect about y equals x. So maybe let me make this line longer. And we end up with the graph of f inverse, okay? But how about if I now reflect this about the line y equals x? So let me say that. So reflect about y equals x. I know that what I'm going to end up with here is going to be the graph of the inverse function of f inverse, okay? But the point is, if you do a reflection and then you do that same reflection again, and you can try this, what happens is you end up with the exact same thing you started with. So two reflections actually cancel each other out. So in other words, the graph I'm actually going to end up with is actually going to be f, because two reflections, two identical reflections, cancel out. So perhaps I should explain what I mean by the statement in red. If I actually take, say, some coordinate system, and if I consider the line y equals x, and if I just take some point, so let me mark a point here, so that point there, and let me call that point A, and let me reflect A to get this green point here, right? And the reflection is about the line y equals x, obviously, to get the point A prime. So we see what's happened is A has basically gone to A prime, right? Following a reflection. So, but if I do that reflection again, so if I do the first reflection, you know, the blue point goes to the green point. But if I now do another reflection about this line here, the green point is going to go back onto the blue point. So let me mark that maybe in an even different color. So I can come back here and say, you know, I've got A double prime. So A double prime happens to be the same as the point A that we started with. So in other words, two reflections basically cancel out, which is precisely what I've said here. Okay, so let's go on and take a look at fact 5. So fact 5 is technically not on the A-level syllabus, but it's an easy enough fact to get one's head around, and it's actually also really powerful. So let's see what it says. It actually says if a function has an inverse function, then it must be unique. So if a function has an inverse function, then the inverse function must be unique. Okay, so let's see a quick proof of these, right? So let f of x be a function which is invertible, right? Now suppose that the inverse of the function f is not actually unique, right? So suppose f of x has two inverse functions. Okay, so let's label them f1 inverse and f2 inverse. Okay, now what that basically tells me is I've got to have f1 inverse of some input giving me some output, but of course if I give the same input to f2 inverse, then that's going to give me the exact same output, right? They have to, because this function here originally has a unique pair of inputs and outputs. So given that these functions here are inverses, then by definition of the inverse functions, both of these basically take each of the pairs of inputs and outputs and just swap the order. So they make the outputs to be the inputs and the inputs to be the outputs. And so if you actually do that, they're going to give us, in both cases, the exact same pairs, right? So if that's necessarily going to be the case, then what that tells me is f1 inverse of x actually has to be equal to f2 inverse of x. And if you now go back maybe to a few videos ago, I'm not too sure exactly when in the series on functions, we actually gave a definition for when two functions are equal. Now, two functions are precisely equal when they do the exact same thing to the inputs, right? And that's precisely what's happening here, okay? So from here, I can just go on and say that actually f1 inverse has to be the same as f2 inverse. So in other words, I don't actually have two inverse functions. I've only really got the one inverse function. The two inverse functions I actually wrote down are no different, right? So let me just say that. In other words, there is only one inverse function. And that completes the proof. There are more technical ways of being able to write this down and express the same sort of thing, but I think that's fairly simple. So let's move on. Before moving on to actually look at concrete examples, let's quickly take a look at this interesting fact here. So if I take f of f inverse of x, that actually will always be the same as f inverse of f of x. Okay, so let's see why this might be true. So let me start by saying, let me say y is f of x, right? So this is just a standard way of writing a function. And then I can say, let me apply f inverse to both sides, right? F inverse is a function. I can just apply that function to both sides. That's completely allowed. So I say f inverse of y is actually equal to f inverse of f of x. And now this is where life gets a little bit more interesting, because we had something like this earlier on in the video where we actually showed that if you take something, you apply f to it, then you apply f inverse to it. That's the same thing as, you know, just having the thing you started with, because the f and the f inverse effectively undo one another. Okay, so here's the first important part of the proof. So we've actually managed to arrive at something which is quite important. Let me actually put it in a box. Okay, this is nothing other than the definition of the inverse function, because if I go back to our initial statement here, we have some input, and then the function acts on the input to give me some output. And what we have here now is our old output is now the input, and then a new function acts on it to give us our old input as the output. So this new function has to be the inverse function. Okay, so nothing too sort of strange there. So, but now to the statement, let's actually apply f to both sides. So let's actually do this. So I've applied f to the left-hand side, and let me also apply f to the right-hand side. Okay, so Now look at the right-hand side carefully and look at that thing there. So we know what this thing here actually is. Well, f of x is nothing other than y, so I can just write that down. And now look, we've actually got something here which is rather interesting, okay? And also, it's not that different from what we have here, right? The only thing that's perhaps different is the fact that here you've got f inverse of f, but here you've got f of f inverse. And in fact, we were looking precisely at swapping the order of sort of function and the inverse function around, and we've sort of managed to do it. So you might now worry and say, well, there's a y here, but there's an x here, and so we've got an issue here. We've got to actually somehow work harder, but that's not quite true, because actually, if you think about what functions are, so I mean, this was described in the very first video on functions in the series on functions, I believe, which is what matters is what the function is doing, not what you call the input, right? So in other words, what we have here is we've got something like this. So let me put a box here for whatever is going in, and let me put a box here. So the reason why I put a box in is because something is going to go in, and in fact, given what we have here, the exact same thing is going to come out. Okay, so in this case, I've just happened to call the thing going in y, but actually I could have called it anything I wanted. Okay, so the point is, of course, we're dealing with real functions. Both x and y are going to be real numbers. So in this case, real numbers are going in and real numbers are coming out. But more importantly, the number you put in is the exact number you're going to get come out. Okay, so whatever's going to be here is going to be the exact same thing that's going to be here. So I could basically write this in this form. I can write this in this form, but that's of course no different to what I have here. So now if I label these statements 1 and 2, I can say, putting 1 and 2 together, what we basically have is f of f inverse of x is exactly the same thing as f inverse f of x. Okay, so this basically completes the proof. And the remark I actually want to add is twofold. So the first remark is, actually we've done something a bit more. We've not just shown that they're equal, we've actually shown this, right? And the reason why we know this is true is because we have it here and we have it here. So in fact, the point is, if you do f of f inverse or f inverse of f, so the f here cancels out the f inverse, and in the other case, the f inverse cancels out the f. Okay, so that's the first remark, and you do need to know this for the A-level syllabus actually, which is why I've included it as a fact here. And the second remark is basically, in the video on composition of functions, I said that the order in which you compose functions really makes a difference. And f of g is not always the same as g of f, right? But here's an exception, right? That is, f of f inverse is actually going to be the same as f inverse of f, okay? And in fact, they're going to be identically equal. So I can write that down. So with sort of inverse functions, you can swap the order around and nothing changes. Okay, so I think that's a good place to move on to some concrete examples. So let's take a look at the first proper example. We have to basically figure out the inverse function for this function that we're given. So let's see how we might do this. So solution. So suppose I say that y equals f of x is my initial function, right? And we've already seen actually in the previous fact, no less, or in the proof of the previous fact, that actually if I take the inverse function to both sides, then this is a sensible way of actually writing down the inverse function. So in other words, this tells me that if I actually just have x equals something in terms of y, then whatever that thing is in terms of y in totality must be my inverse function, okay? So what I'm going to do is I'm going to use the fact that y is f of x and f of x is this, and then write down y equals 3x plus 1. And from this point onwards, I'm going to rearrange this to be able to get x equals something in terms of y, okay? So I'm going to say, let me rearrange that. Let me take away 1 on both sides, so I actually have this. And let me actually go on and divide both sides by 3, so I actually end up with this, okay? And now we see, so I have something purely in terms of x, and so this thing here is purely in terms of y. And of course, what I can now say is, since x equals f inverse of y, and x equals y minus 1 over 3, then f inverse of y is actually y minus 1 over 3. And we're basically done. This is really our inverse function. So the only thing I would like to say is actually the question requires us to write down the inverse function in terms of x, and this is written in terms of y. But obviously, as we've already seen in multiple videos, really, that it really doesn't matter what symbol you give to the input or the output even, okay? The important thing is what's the function doing. So what the function's doing is whatever you put in, the function's going to take away 1 from that, and then it's going to divide all of that by 3. So suppose I decided I actually wanted to put in x, the function is going to take away 1 on that, and it's going to divide the whole thing by 3, right? So this thing here is basically our inverse function, and we're done. We can indeed do a quick check to make sure that this makes sense. So let's try and figure out f inverse of x. So let's say that. It doesn't really matter which way around you compose this. And what we're going to do is we're going to say f inverse is what we've worked out. So let's put that in. It's going to be x minus 1 over 3. But what is f? F is going to triple the input, and it's going to add 1. My input is all of that. So my f is going to triple all of my input, which is x minus 1 over 3. And then it's going to add 1. Well, when I do this, what happens is this 3 in the numerator and 1 in the denominator actually cancel. So I end up with this. And then plus 1 just gives me that. And we know that's the right answer because this is exactly what we proved must be the case in fact 6. Okay, so we've managed to do this. I should perhaps add a remark that there are other ways of doing these sort of questions. Another way of doing this question is you start with y equals, say, 3x plus 1. And what you want to say is because the inverse function swaps the role of x and y, so let me write that, inverse function swaps the role of x and y, we have that we can actually go to this thing here, and because we want the inverse of this, we swap the roles of x and y. So we have that x equals 3y plus 1 must be the case, must be satisfied by the inverse function. Okay, and now it's really just a matter of solving this for y, right? So let me do that. So we just basically say x minus 1. So let me do that here. X minus 1 equals 3y, and then that tells me that y is actually equal to x minus 1 all over divided by 3, and therefore this is the exact same thing as saying my inverse function is actually x minus 1 over 3. So we managed to work this out another way. So yeah, so feel free to either use that approach or to be able to use this approach when working out inverse functions. But really, it's the same idea, regardless of how nasty this sort of thing gets. Okay, so I'm not going to cover many more examples on this. This is a fairly straightforward thing. So let's take a look at example 2. Example 2, we have to basically show that the function f of x equals x squared can be inverted, but under restricted domains, right? So let's think this through. So we know that, for example, if I go to the graph of y equals f of x, let me maybe get a grid here. So if this thing here is our graph, f of x equals x squared, we know that this is basically many to 1. We can see this, right? So we've got, for example, we've got this input here giving me that output, and we've got this input here giving me the exact same output. So it's definitely many to 1, which basically means cannot be inverted, right? But that doesn't mean that it cannot be inverted at all, right? So what I should say is it cannot be inverted over its entire domain. So in other words, if we start to change the domain, so say if we actually decide to throw out, say, let me say this part here. So let me throw all of these out. Then what happens is basically this part of the graph can be deleted, right? So let me get rid of that. And now you see all of a sudden this is actually 1 to 1. Okay, so for x being bigger than or equal to 0, f of x equals x squared is 1 to 1. and thus can be inverted. So this is our restricted domain. Let me say that here, maybe. So this is our restricted domain. And unsurprisingly, the inverse function is actually going to be f inverse of x is actually going to be the square root of x. Is the inverse function. And of course, this is only true for the inputs actually being positive, and I should say this is a positive square root that we're actually going to take. Let me actually show you algebraically that this is going to be the inverse function. So let me just say y equals x squared, and we want to rearrange this. So let me go and take the square root of both sides. So I take the square root of both sides, and I just want to emphasize I'm taking the positive square root. So when I take the positive square root of both sides, I actually end up with the positive square root of y is actually equals to x, and that tells me that x is actually equals to the inverse function, and obviously this is in terms of y so far, so it's this. But since it doesn't really matter what you call the input, we can just say therefore f inverse of x is just the square root of x, and of course we're taking a positive square root. This is basically our inverse function. So we've managed to work out our inverse function. While we're here, it's probably worth actually doing a quick graph as well. So let's do the line y equals x. Okay, so this is the line y equals x. And then the graph of the inverse function is going to look something like this. So it's going to look something like that. Okay, so f inverse of x is actually equals to the square root of x, and of course all of this is for our restricted domain. So we've managed to do this question. Let's go on and take a look at the next question. So let's take a look at the last example. We're given a function f of x. It's a cubic, and the function is defined for all real numbers. Okay, and the example requires us to work out the graph of the inverse function, and then the second part of the example requires us to work out a solution for the equation f of x equals f inverse of x. Okay, so let's take a look at the solution for the first part. So let's do this, and of course we have a graph of f of x here. It's a rough sketch really. We know how to get the graph of f inverse, so let's get the line y equals x. So maybe we can do something like that. Let's extend it back. And we want to carry out a reflection about this line, right? So let me take a different color. So I know, for example, anything on the line of reflection is going to reflect on to just remain there. It's not going to change. So let's carry out a reflection. We know that this point here is basically going to end up and be somewhere like there. So let's join the red and the blue. So we're going to get something like that. And then we also know that this point here is basically going to go across and end up here, right? And we know that this point here is actually going to go across and end up maybe here somewhere, right? So let's now join these points up as well. We actually will end up with something like this and like this. So it's not the best of sketch, but I hope it gets the sort of the message across. So this graph here now is the graph of our inverse function, and of course I should have marked that this line here was actually the line y equals x. So we've managed to do the first part. Let's take a look at the second part. So we want to solve f of x equals f inverse of x. Okay, so the slightly harder way of doing this is to actually start with y equals 1 over 27 x cubed plus x minus 8, and then to be able to sort of figure out the inverse function, and then to basically substitute into star. Let me say star, and we can mark this a star, and then to be able to solve, right? That's completely fine. That's a logical way of doing it, but that's not really the most sensible way of doing it. The more sensible way of doing it is to actually see the point at which f of x and f inverse of x are actually going to intersect is the exact same point at which f of x and y equals x is going to intersect. So to solve this equation, right, it's easier, let me write it here, easier to solve f of x equals x, right? And we get the same solution. We get the same solution as f of x equals f inverse of x will give. Okay, so let's now do this. So maybe let me make a bit of room here. Okay, so I want to do 1 over 27 x cubed plus x minus 8. This is my f of x. I want to set it equal to x. And then obviously this is easy because we just cancel this thing and that thing, right? And then we can go on and say 1 over 27x cubed is actually 8, which tells me x cubed is actually 8 times 27. And I can take the cube root of that and it gives me, I believe, which is going to be the cube root of 8 times by the cube root of 27, which is going to be 2 times 3, which is actually going to be 6. So we've managed to work out our answer very, very easily this way. Okay, so I think that's probably a good place to end the video. Thank you for watching. If you found this useful, then please do hit the like and subscribe buttons. As always, do let us know in the comment section as to what you would like to see more videos on, and we will see you in the next video.